let me just repeat something, right? Last thing that we discussed yesterday was the S-wave amplitude, right? The S-wave amplitude. Yeah. Oh, great. 2 minutes. Very, very good. Yeah, 4 more person. 5. Okay. that's incredible, right? Uh, last thing we did yesterday was to discuss. We mentioned phase shifts, right? And we mentioned unitarity. You remember, right? So the S-wave scattering amplitude in the case of elastic scattering, elastic scattering, is a function of just the energy, the center of mass energy. So then you have something like that. Okay, so this is the incoming center of mass momentum for the initial particles, and this is the P prime is the center of mass momentum for the outgoing particles. The cross section, the differential cross section, this angle is theta. Okay, is just the modulus square of. Okay, I use this notation, which is very handy. No, which is very handy, which is the amplitude from going from P to P prime. P is the initial momentum and P prime is the final momentum, right? So then, if you remember, the idea is that you can do a partial wave analysis of this scattering amplitude. Well, of course, I am forgetting spins and things like that. That makes all the expansions a little bit more complicated. I am doing this thing, okay? So it's spinless, it's a scattering of spinless particles, okay? So this can be written something like the sum from L equals 0 to plus infinite to L plus 1. And then what happens is that all angular dependence is encoded in a Legendre polynomial. And here you have this partial amplitude which depends just of the energy. And the energy is just 2 mu k, and k is just the modulus. I am doing correctly. Sorry. K is 2 mu E. Okay, and this is the energy. And K is just the modulus of both the initial and final momentum. This is elastic scattering, IB going to AB. Okay, so this object, when you can define the phase shifts. I will pay attention only to S wave. And you can define the phase shifts in this manner, right? Okay, and these are the phase shifts which are a function of the energy. Okay, good. So you remember we did very quickly, but we did it already. So you can write this thing as, if you just look at to the inverse of this scattering amplitude, it can be written like K cot delta minus IK. Okay? So the imaginary part of the inverse of the scattering amplitude is just given by the momentum, by K. Okay? It's just given by the momentum by K. Okay? This is unitarity. This is elastic unitarity. All the physics, all the theory comes into this thing, right? The physics tells you, allows you to predict the phase shifts, and therefore allows you to predict K cot of delta, right? The cotangent of delta, right? And then typically what happens is, if I look at soon, no. What happens is that you will see in the books that there is something called effective range expansion. Effective range expansion. That is allows that say, okay, K cotangent of delta can be written, well, you can show that this object that is not a function of K, it's a function of K squared. So it's to say it's a function of the energy, right? It does not depend on K, it depends always on K squared. And this is very important because all the stuff of the Riemann sheets, okay? So this object in principle can be written something like that. Okay? And this is the scattering length, and this is the effective range. But here you have dots. Okay? So it's an expansion. All the things about Riemann sheets, so comes because you have dependence which are linear in the momentum, right? So then K is just the square root of the energy. And because it's the square root of the energy, then I think that we have here one friend who is working in in dispersion relations. So if I look at to f minus 1 and I put set because I am going to the complex plane. I am going to the complex plane. Okay. So I am taking complex energy. What happens is that you have the so-called right hand, yeah, you have a branch point. In this case is, is for energy 0 because I am assuming, well, I am taking the origin of energies in the sum of masses, right? And then this is really, this blackboard, this is just the kinetic energy, right? So there is a discontinuity. There is a discontinuity, right? Because it's not the same thing if this is the scattering line, and this is not the same thing if I am in the first quadrant, is if the energy is here, or if the energy is here, right? There is a discontinuity, and this is the so-called right hand cut. Okay, and everybody understand that this is not the same thing. Yeah, sure. F minus 1 depends on K, right? Okay, so then if I compute well, there is a 2 mu here, right? I am computing, okay, I am computing the momentum, right? Because, okay, so this is essentially, the argument of this is 0. The argument of E plus I0 is 0, while the argument of E minus I epsilon is 2 pi. Because I am in the fourth quadrant. Therefore, here I am going to get essentially 2 mu E, where here I am going to get minus 2 mu E. Right? Because square root of z is something like the square root of the modulus of z, and then you have I to the argument of z divided by 2. Ah, okay, it's already. No, I haven't. No, it's still waiting. Ah, okay, good. So you understand? So there is a discontinuity. It's not the same thing if I compute f minus 1, the energy E plus I epsilon, or if I compute f minus 1 and the energy A minus I epsilon, right? The difference comes in the imaginary part. Because why comes in the imaginary part? Because the thing that is proportional to the momentum that is creating this problem is in the imaginary part. So this is twice I, the imaginary part of f minus 1 computed in E plus epsilon, and this is twice ik computed in E plus I epsilon, right? Okay, this is the right hand cut. And now I can share. Okay, good. Now I can share. Okay, good. On top of that, you may have also something that is called left-hand cut. And the left-hand cut has to do with the dynamics. I cannot enter into details, but this thing has to do with the dynamics. And the left-hand cut is contained in the potential, right? The left-hand cut is contained in the potential. For instance, suppose that you have nucleon, well, pion exchange. So the left-hand cut comes from situations where you can put on the mass shell this exchange pion, but that cannot happen for energies above threshold. It happens for negative energies, right? It cannot happen for energies above threshold because you cannot put everything on the mass shell, right? And this is the origin of the left-hand cut. So the left-hand cut contains the dynamics. And that's all what I want to tell you about these general things. Okay, so then this is PDG. Okay, this I have extracted from the PDG, right? So what I want to study is, okay, you will see that since something like 10 years ago or something like that, in the PGD, you will find no 2 poles. No one pole, no only one lambda 1405, but appear a 2-pole structure. And this is what I want to discuss with you here. I mean, if you have the opportunity to look at that the PDG editions of something like 20 years ago, you will see that you will find only one pole at this in this energy region. That it was called lambda 1405. But after all the studies that have been carried out in the by the community after 2000, now in the PDG appear 2 poles. Okay. Then I will also, it's just in the strange sector, I mean, today we will also discuss these cascades, the cascade 1620 and the cascade 1690. And then, well, I will show you that they are somehow related. Okay? So we have mentioned several times that these are P wave, these are called P wave baryons, because of the parity, because you need to insert 1 unit of angular momentum. We have already said this thing several times. Okay, so my objective today, my only objective today is try to give you a flavor. This is in the PDG, you have a compilation of the properties of particles, but also there are some reports, some specific reports about things which are of special interest. And there is one that it was written, well, the latest version was written in 2021, and that case was that was written by Hyodo-san and Ulf Meissner, referring to the pole structure in the lambda 1405 region. And my goal today is, okay, just to give you a flavor of what is the meaning of these two paragraphs, right? I don't want to do something, anything else than that. Okay, it says that the lambda 1405 is an archetype of what is called dynamically generated resonance, and then it says that a perturbative calculation is not applicable, right? And KPT needs to be combined in a non-perturbative resummation technique and solving the Lehmann-Schwinger equation, right? Somehow we already spoke about these elements yesterday, right? So we said, oh, what we have to do is this, okay? What we have to do is this. We are going to consider the scattering of Goldstone bosons of baryons, okay? I draw these sort of diagrams yesterday. You remember? Baryons, so we are going to work in SO3, so baryons involve nucleons, so nucleons, so the 1/2, so the baryons that we are going to consider are baryons with a spin parity 1/2 plus that are in the octet, right? I have drawn the plot, the octet many times, right? You have neutron, you have proton. Here you have psi 0. No, sorry. You have psi minus, you have psi 0, you have the psi plus, the sigma plus, sorry. And here you have the lambda, and here you have cascade minus, and here you have cascade 0. Okay? And okay, and don't get confused. I mean, when I say lambda, this is not the lambda 1405. The lambda that I have here is, you see, is that one. That you were right, 1116, right? Instead of 1115. Is the ground state of the system of two light baryons and strange, okay? And then I am going to consider the scattering of these baryons with the Goldstone bosons related with the pion, right? So then I am going to consider here I have here I have the kaons, sorry, the antikaons. I have the antikaons, so I have the K minus, I will have the anti-K 0, then here I have the pi minus, the pi 0, I have here the pi plus, here I have the K0, here is the K plus, and here I have the eta, okay, the eta meson. And then I am going here, there is a word that is very important, coupled channels. What does it mean, coupled channels? Okay, coupled channels, I mean, we saw yesterday, right, that if we pay attention to the strangeness -1 system, right, sector, because we are talking about the lambda 1405. So you remember we were talking about pi sigma, k bar n, and then lambda eta, and then k on cascades. There are these 4 channels, they have a strangeness -1. So coupled channels means the following: is not as easy as elastic. It's not as easy as elastic. So what here you have is, for instance, you say, okay, if you say that pi sigma is your channel 1, okay, so T1 for T11 it contributes not only pi sigma, it contributes not only pi sigma, which is the potential, right? So it contributes, okay, so we may have a loop involving only the pi sigma channel, but I can have other loops contributions where I have pions. I start with pi sigma, but now here in the intermediate state, I could have k bar n, and then the k bar n decays into pi sigma. This is one loop, right? It's called coupled channels because to solve, okay, and then I have put k bar n, but you could put any of the intermediate states, okay? So then you realize that you need to solve a problem in a matricial problem, right? Because to get this thing, you need to consider also if, okay, if I consider only 2 channels, you need to consider also T12 and T22. For instance, in T12, that will be pi sigma going to k bar n. Okay? But you can have pi sigma going to pi sigma, loop the pi sigma and then k bar n. Or you may have pi sigma, then here you have a loop k bar n, and you end up k bar n. Yeah, tell me. Yeah, but I know, and also the right-hand cut. Also for the right-hand cut, because okay, here at the left, I was just considering elastic scattering. I say AB going to AB, right? So this is going to be a little bit. It's not going to be as easy as this, because I am going to have something that is called inelasticity, right? Because I could have strength in the pi sigma and it disappears because it goes to the k bar n, right? So then the modulus of this matrix is, or the element 1 of this matrix is not 1. It's just inelasticity. So you need to consider everything, right? Thank you. And then T22 will be, but these to all orders. T22, okay, so it will be k bar n, k bar n, but then it will mix with another channel, k bar n, then here you have pi, you have sigma, and k bar n, etc., right? So you understand that you have to solve this matrix equation. That's the meaning of Kaplan channel approach, right? So it's a little bit more complicated. But the idea is, okay, if I solve these equations, now I need to be a little bit more careful, because we already wrote this sort of equation yesterday, right? But we need to be a little bit more careful. Why? Because both V and T are matrices. And because are matrices, when here I said 1 over minus Vj, I means the inverse of the matrix 1 minus. So yesterday it was a bit. Yesterday I was a bit. I was just working in one channel, but the T matrix. Sorry, the Lyman-Swinger equation, it will be the same equation, but the only thing is that now V, T, and G will be matrices. G is the loop. G is the loop, right? B is going to be a matrix, right? And for instance, okay, I am let's pay attention to each of the pieces of this equation. V is the matrix, is the potential, and is the thing that is determined in principle by chiral symmetry. A leading order is given just by the Weinberg-Tomosawa term, right? Look at that. This is B. Okay, you see? This is B. It's a 4 by 4 matrix. It's a 4 by 4 matrix, and this is this thing here. It's a 4 by 4 matrix, and this thing is being determined by the Weinberg-Tomosawa term. We deduce the Weinberg-Tomosawa term for pi n going to pi n, but in principle, this can be extended to SU3, and you understand that this is okay. So what does it mean, this? This minus 3 means that, the first minus 3 that you have here means that this potential here is minus 3. K bar n going to K bar n is minus 3 times this function of energy. Okay? So what does it mean, the square root of 3 over 2? What is the meaning of the second entry? In the first row and second column, square root of 3 over 2. Look at that in Blackboard. Is the pi sigma K bar n potential, right? What's the meaning of minus 4? Is second row, second column, is pi sigma going to pi sigma. This is very, very interesting. This is just the lowest order, which is Weinberg-Tomosawa. But in principle, it depends how strong you are. You can go beyond the lowest order, which is Weinberg-Tomosawa, incorporate more derivatives of the boson fields, and that will give you something, for instance, the next to leading order, right? And then there will be other corrections. But these corrections, because if I told you that all the couplings with the pions are derivatives, right? So it will be proportional to the pions. With Goldstone bosons are derivatives, and all kaons are Goldstone bosons as well, right? So all the couplings are derivatives. So then it will be proportional to the momenta. So if you are close to threshold, in principle you have a well-defined expansion. Okay, but things becomes a little bit complicated, because the Weinberg-Tomosawa I only had, is very powerful. I only had that it was the pion decay constant. And I could determine the pion decay constant just by looking at the pion lifetime. I know this parameter. But then when I go to the next order, there will appear some more unknown constants. But you can fix here or you can fix somewhere else. But the nice thing about that is, that is systematically improvable, right? So I have a power content and I can do the things as accurate as I wish and as strong I am. Okay, so okay, I will continue this lecture till something like 10:15, and then I will disappear because I have to take the plane. But Dr. Xiankun Don, I have asked him to deduce for you this matrix. Okay, just from the Weber-Tomosawa term in the SO3, he will deduce for you this matrix, just to get to see what is going on. Okay, so we know what V is. Okay, what about G? What about G? G is the loop. G is the loop, right? G is going to be a diagonal matrix, right? Because in the loop I have pi sigma, or I have k bar n, right? Or whatever it is. It's going to be a diagonal matrix. Okay? It's clear? And all of you, so G is going to be a diagonal matrix. So G is going to be G pi sigma 0, 0, 0, 0, G k bar n 0, 0, 0, 0, G eta lambda 0, 0, 0, 0, G k on cascade. Okay. So those who have taken a quantum field theory course should know how to compute G, right? So okay. So what I have is, okay, I have a total momentum P. I have a total momentum P. So these are the typical Feynman rules. This is an internal momentum Q, and I should do the integration over Q. And this another line here has momentum P minus Q. Okay? And typically, this is the total momentum that I have, P. Okay? So then, okay, just to make the thing easy, you can consider something like that. Okay? That the zero component is just the square root of S is the Mandelstam variable, right? Is the energy in the center of mass frame. And then I have zero momentum, okay? Very important, very important. It's very small here, but it's one of the most important things, plus I epsilon. Plus I epsilon. Those who have followed a Feynman a quantum field theory course, you know, this plus I epsilon is really essential. And actually, here I show you that is really essential, the plus I epsilon. So actually, in this, when I solve the Riemann-Schwinger equation, then the scattering line, so the scattering is obtained when A with the energy is above the right-hand cut. So it's really essential, the plus I epsilon, okay? And then someone may complain and say, okay, if this is a baryon, the baryon is a fermion, so then Juan, you are forgetting the Dirac structure, right? You are forgetting the P slash minus Q slash plus M. I am not forgetting that. I am not forgetting that because I have incorporated, this is the origin of this energy factor here, right? This is the origin of this energy factor here. And then here you see the problem. Can I do this integration easily? You know, you say no. Someone say that one can do this integration easily? We just have a mathematical, we just put this thing, or we just take Simpson or whatever it is, and we do this integration? No, why, Daniel? Because a divergence, right? A divergence, right? You have in the ultraviolet, right? It diverges in the ultraviolet. It has an ultraviolet divergency, right? Because for large momenta, then you have 4 powers here in the measure, and then you have 4 powers in the denominator. So this is a logarithmical divergence in the ultraviolet. So that means that you need to renormalize this divergence. And that's complicated. That's complicated just to do it properly because you need to renormalize this divergence. And I repeat once more, these divergences you are working in QCD can be reabsorbed in your parameters. If you are not working in QCD, this divergence should be, it gets compensated by your new contact terms that also will diverge, and then the finite, when you sum both things, the finite part becomes. So suppose that they have only one channel. Suppose that they have only one channel, and you will see. If you have only one channel, you remember, if I have only one channel, this is what we discussed yesterday. T is V, 1 minus Vg. And that can be written like T minus 1 equal to V minus 1 minus G. Okay? So I am not doing properly the things because I am making everything very simple, but I want you to give a flavor of what is going on. Okay, so here we have a divergence, no? Here we have a divergence, but this is unobservable. So T should be free of divergences, right? So how can I compensate the divergence in G? With V. Yes, with V, right? I can compensate the divergences in G just by putting another divergence in V minus 1, such that the subtraction is finite. And the finite part, I don't know it. I should fit to somewhere else. Is the difference with QCD. You understand what I am saying? And this divergence, what happens is, okay, that if I have my leading order, then what happens is that I need really to add an S2 leading order that it will contain this divergence and it will compensate the one in G. So this is renormalization. You could imagine this is a little bit more complicated when you are working with matrices, right? Okay, then there is one important thing is, okay, right, okay, so this is the particle actually quantum field theory. This is the two particle irreducible amplitude. This is not a potential. In quantum field theory, this is the two particle irreducible amplitude. So this object contains the left-hand cut. This object contains the left-hand cut. While the unitarity cut, the right-hand cut is just provided by G. And actually, the imaginary part of T minus 1 is just minus the imaginary part of G, right? And then the imaginary part of G is proportional to the momentum. There is some factors, look, between F and T, there is some factors because in quantum field theory, this sigma, the omega is 1/64 pi square S T square. So there are some factors between T and F, right? I think, I don't want to make a mistake, I think that T is minus 8 times pi square root of S of F, right? That's the reason why they say proportional, because the imaginary part of T minus 1 is proportional to the imaginary part of F minus 1 and it should be the momenta, right? So Xiang-Kun later is going to take take this propagator, is going to do the integral over energies using Cauchy's theorem, just looking at the position of the poles, and then he will be left with an integral over D3Q, but the imaginary part, it will be possible to compute the imaginary part, thanks to the I epsilons. Yes, tell me. Yes, yes, this is what I have written here. Yeah. No, no, because this equation is equivalent to that one. And here you see is, well, you may, I mean, this is sometimes it's difficult to see that it seems that this contradicts the N over D picture, right? Because in the N over D approach, you have that the T matrix is just one function that has a left-hand cut in the denominator divided by one function that has a right-hand cut in the denominator, right? And you may think, Juan, this is not true, right? Because I have something with left-hand cut in the denominator, and in the denominator it looks like that there are both, that appear both, the left and the right. But it's consistent. It's consistent, right? But B now is about left-hand cut, because left-hand cut is dynamics, and the dynamics is in V. Unitarity is right-hand cut, and it's kinematics, full stop, it's G. It's the finite part of G. And then, thanks to this I epsilon, we will find. And then it's going to be proportional to K, to the momentum in center of mass. Okay, so then we have mentioned V, we have mentioned G. So we can write that, what can I do? I can put here the identity minus VG T equals V, right? And then I can write 1 minus VG minus 1 V, this is T. So the message is that you have to be a little bit more careful because you are working with matrices, and this is what I said. This should be understood as the inverse of the 1 minus BG matrix. And then you will see, okay, you will see, well, if you look at my expressions, you will see indices J, isospin, hypercharge, is because I can do these things sector by sector, because isospin is a good quantum number, hypercharge is strangeness plus baryon quantum number, and J is the angular momentum. So then I can do in a sector. Actually, when I am working, when I am trying to get the lambda 1405, I am in the J equals 1/2 sector. I am in the isospin 0 sector, and the strangeness, I think, is 0 because it's baryon number 1 plus strangeness that is -1, right? This is the origin of these numbers. So the idea is, now we look for poles of T. This is a typical one example. Here you have, this here is the first quadrant of the first Riemann sheet. This line here is the scattering line, the blue one. And here you have the fourth quadrant of the second Riemann sheet, because the second Riemann sheet is defined just by continuity. It's just defined in such a way that, okay, here I am in the first Riemann sheet, I go through the cut, and then I end up in something which is different, right? But then what I do is I take the second Riemann sheet in such a way that is continuous, right? The fourth quadrant of the second Riemann sheet is continuous with the first quadrant of the first Riemann sheet. And then if I have, so this is, I think, is very intuitive. Why a pole in the second Riemann sheet? Why a pole in the second Riemann sheet? In the fourth quadrant of the second Riemann sheet has any importance. Why is important this? You will see in the plots. This is the first Riemann sheet. And I want to know what is happening here. The scattering line. Okay? The first quadrant. This is the fourth quadrant of the second Riemann sheet. They are not connected. If I have a pole here that is forbidden by causality, I don't care. Okay? I really don't care. But what happens now is the first quadrant of the Riemann sheet, or the first Riemann sheet, the fourth quadrant of the second Riemann sheet are it's continuous, right? So now, if I have here a pole, as in this plot I am showing you, yeah, if I have here a pole, you see this pole in the fourth quadrant of the second Riemann sheet, it produces an enhancement, a bump in the scattering line. So it produces something, some signature in the cross section. In this case, is a maximum, right? A local maximum. So this is the way that allows you to say, okay, this resonance that I am generating there are producing something. You understand what I am saying? Okay. A bound state will be a pole just in the first Riemann sheet real here. And here we don't have a bound state. We don't have a pole in the first Riemann sheet below threshold. But if I had it, it will produce an enhancement. It will produce an enhancement very close to threshold, right? Eh? If with a width, it could, okay, this is a strong interaction. So it could have, well, it could decay, for instance, it could decay just through weak processes, right? Because here I am talking only about strong processes, right? So, and then the position of the pole in the complex plane, it tells you things about the mass of the resonance and the width of the resonance, right? And then the residue of the pole tells you things about what is the coupling of this resonance to the channels, to GI, to the channel. So what is the coupling of this resonance to the pi sigma channel or to the K bar? So suppose that now you are working in something like that. Well, you could say, okay, I have pi sigma, then I produce my resonance, pi sigma. So the residues are providing you this coupling, right? So why I have GI, GJ? Okay, because here I could have K bar N. So then this coupling here will be different. Okay, does it make sense to you? All what I am telling? More or less, you get a flavor of what is happening? Okay, so I am not going to say anything about renormalization because I don't have time, and then I think it's going to be useless. One easy thing, you just plug in an ultraviolet cutoff. Is one thing. I mean, you could use dimension regularization as well, but one way to do it is, okay, in the D3Q integration, I just plug in some hard cutoff. So that means that you are not going to consider momenta larger than this hard cutoff. This is one way of renormalizing the things. Okay, so that really will mean that you put here some hard cutoff, so you are predicting some NLO terms which are function of this cutoff. Okay, so I don't have time about that. This is what I told you, right? That later, Dr. Sashankun, will work a little bit with this propagator, and then he will show you that the imaginary part of this propagator is proportional to the momentum. Okay, the momentum is here. It was just, okay, I wrote several times that the momentum is just 2 reduced mass times E, but this is in non-relativistic kinematics, right? You know that in relativistic kinematics, the momentum is lambda 1/2 divided by twice square root of S, and lambda is the Chilean function, right? So the momentum in relativistic kinematics, the center of mass, well, where I don't want to, okay. So the momentum in relativistic kinematics is going to be in the center of mass frame is 1 over twice square root of S, lambda 1/2 of S, m squared. This is the momentum, right? So you have two masses, A squared and B squared. And lambda x, y, z is x squared plus y squared plus z squared minus twice x, y minus twice x, z minus twice y, z. Okay, this is kinematics. This is relativistic kinematics, right? And everything, all this stuff here is kinematics. Okay, so this is one example. What can be done? You just have data for sigma pi going to sigma pi, for k minus proton going to eta lambda, k bar n going to pi sigma. This is data from experiment, from cross section. You just fit, because when you have divergences, you need to renormalize the divergences. It's like that you need to put NLO terms. So there are some undetermined constants. You just fit the constant to reproduce. You just fit the constants to reproduce the data, and then automatically, this is okay. This is a paper 22 years ago, and we were not the first. I mean, somebody, there were a paper done a 1 year before, essentially doing the same thing. This is the first Riemann sheet. This is the second Riemann sheet. This is the scattering line. And then what we find is, okay, we find no one pole. Well, the plot those days had less quality than now. But you see that we found 3 poles, right? We found 3 poles. 2 of these poles around the 1405 energy, right? That one is narrow. This is much broader. And there was a third pole around lambda, around 1670, okay? And then, well, the thing is that we also mentioned this thing yesterday. K bar n, the K bar n channel is closed, because the K bar n threshold is above, so it's closed. So these are resonances because they can decay into what? Into the pi sigma channel that is open, right? And then what happens is that the narrow resonance has a small coupling to pi sigma, and because it comes from the approach, and because it has a small coupling to pi sigma, then its width is small. While the another one, it has a large coupling to pi sigma, and then becomes broader, right? Essentially. Here, for lambda 1670, the situation is different, because at 1670 you have K bar n is already open, and then eta lambda is also open, right? Is also open. And then you may wonder, why 3 resonances? It's something that you should be expecting from the very beginning, that you should find 3 resonances. It's SO3 symmetry. It's as easy It's as easy as this. You know what the big Nedeker theorem is? You remember what the big Nedeker theorem is? No? No? Okay. So suppose that you have two angular momentos, J1, J2, and then J1 and J2 can couple to J, okay? And you know that the values of J squared vary between the J1 minus J2 to J1 plus J2, okay? Right? So now you want to compute something like that. J1 and 1, G2 and 2. Then you have here a scalar. You have here some okay. In principle, a scalar under rotations, because I don't need anything else. And a scalar under rotations, for instance, your Hamiltonian, right? And so the big Nedeker theorem tells you that, okay, tells you that all the dependence in N1, N2, N prime 1, and N prime 2 is just a Claes-Gordon coefficient. You remember that? This is just I am saying something. Just a minute. I am saying something wrong. I am saying something wrong. I am saying something wrong. Now if I have J1 and 1, J2 and 2. No. So sorry, I have J1, J2, and I couple to J. Sorry. Is J1, J2, and I couple, J1, J2, sorry. I couple to Jm. And then I have here J1, J2, I couple to J prime, M prime, right? So then what happens is exactly, no, Andrea, I don't remember big Nedeker. It's a Claes-Gordon, so it's a Claes-Gordon J1, J2, J. Yeah. I remember. I have here an operator that is invariant, and I have another operator I have an operator, it's a tensor and the rotations, right? And then you have that all the dependencies, J1, J2, no, is. Sorry, I don't remember. There is something that I am not seeing. There is something that I am not seeing now. Okay, so let me do it in a different manner. So then if you want to compute, if you want to compute the matrix element of J1, N1, J2, N2, and then here you have this is what I am going to need. You have the Hamiltonian, and then you have G1, N prime 1, G2, N prime 2. So then what you do is you plug in here your Claes-Gordon series, right? You say that this is the sum over J of the Claes-Gordon J1, J2, the sum over J and M, the Claes-Gordon J1, J2 give J, So little j, right? Sorry, excuse me, little j. So J1, J2 to give M, and then you have N1, N2, M, and then you have the Claes-Gordon J1, J2 to get, so you have sun over J prime, M prime, so you have G prime, so you have M prime 1, M prime 2, M prime, and then you have J, N, Hamiltonian, J prime, M prime, right? Exactly. And then because this is a scalar, this is delta J, J prime, and this is delta M, M prime, okay? Because this is a scalar. And then appears a reduced matrix element of the Hamiltonian, right? That depends only on J. Okay, appears a reduced, sorry. So what I have done is, okay, I have J1 and J2, then I go to a basis. I go to a basis where I have a total angular momentum J, another component M, and this is the corresponding Claes-Gordon. I do the same thing. I do with the same thing with my ket, and then I take what I do is, okay, because it's a scalar and the rotation, this is delta J prime, delta M prime, times something that does not depend on the third components. It's just, it depends on J, okay? So then at the end of the day, what you have is something like sun over J and M of J1, J2, J, sorry, N1, N2, M squared times J Hamiltonian J. Okay, sorry, excuse me, I am really sorry. Okay, this is the normal thing. And it could be a problem of notation. This is my Claes-Gordon. You may be using a different notation for the Claes-Gordon, I'm sorry. Okay, but here what we have is SU3. So what we really have is, okay, we are just coupling. The role of J1 now is the octet of the mesons. The role of J2 now is another octet, which is the octet of the baryons. Okay, now the thing is, okay, we know in SU2 that if you couple J1 and J2, the possible J's, the allow total angular momentum runs between J minus 1, J minus 1, J1 minus J2, and to J1 plus J2, okay? But now in SU3, it's a different Claes-Gordon series, right? So it happens that if you reduce this product of representations, you get a singlet, two octets, a decuplet, an antidecuplet, and a 27 representation. 8 times 8 is 64, and 1 times 8 is 9, times 8 is 17, 37, no, 1, 17, 27, 37 plus 27, 64. Okay, in the same manner that when you have spin 1/2, spin 1/2, you have spin 0 and spin 1. So it's 2 by 2 is 4, and spin 0 and spin 1 is 1 plus 3 is 4, right? So then, just to say, if you say that your Hamiltonian is invariant and the SF3 rotation, you could do the similar thing. The only thing is that you will have this Wigner-Eckart reduced matrix elements that will depend on the representation that are unknown functions, right? So then what happens is that you will have something like 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 functions that you don't know what the hell are. In the same manner that here, right? That you don't know what these matrix elements are. And these functions will be functions of the energy of your system, okay? Should be just SU3 symmetry. But then, if you assume chiral symmetry, and then you take the Weinberg-Tomosawa, what you are obtaining is that chiral symmetry is telling you the strength of these eigenvalues. because the strength of these eigenvalues, they are obtained just by diagonalizing the matrices, the potential matrices, for instance, right? So then Weinberg-Tomosawa is telling you that there are two octets which are attractive and a singlet which is attractive, while in the rest of the channels are either repulsive or there are no interactions. So that means that here this is what for three cases is attractive, for one is repulsive, and from the rest are 0. Okay, so then what I should expect? I should expect two octets of resonances and a singlet of resonances. I should expect something like, what is this? Yeah, that one. I should expect two octets of resonances and a singlet. You remember that I found 3 lambdas. Okay, I put one lambda in one octet, the another lambda in another octet, and then I have a singlet. And this is a consequence of chiral symmetry, the Weinberg-Tomosawa. Well, you break chiral symmetry. Okay, you break chiral symmetry, and that's the reason why I haven't. I am not going to cover because I don't have time. But you could imagine that now I can do the same business, but not in the sector of the lambda. I can do the same business in the sector of the nucleons, and then you will get resonances. And then what happens is that they don't have the same mass just because you have broken chiral symmetry. And then if you do the same thing in the strangeness -2 sector, you get the cascade 1620 and 1690. And that was important because in the PDG, the spin parity of these resonances was not known until all of these chiral studies were done. Actually, here in the, what is this? What is this? Actually, here in this, I don't know if you can see it. I mean, I can do the same. I can do the same business the same work that I did in the lambda sector. I can do in the nucleon sector, and then I can fit. I can look at the pi n, pi n eta n, pi proton k on lambda. So strangen is 0, and then I find resonances, and the resonances that I find are now the nucleons. And I can do the same thing in the cascade sector, so 2 units of strangeness, 2 units of strangeness. Typical channels that I should consider: antichaon, sigma, for instance. Or I can consider pi cascade. Yeah. And then you get resonances, and these resonances can be identified with the 1620 and 1690. And then it's a consequence of chiral symmetry, the fact that there is no one pole around lambda 1405, the fact that there are 2. Why chiral symmetry? Because chiral symmetry is telling you that there are 2 octets and 1 singlet that provides a attractive interaction, right? Sorry that here maybe just because I had a lapsus. So look at in this blackboard again. It's easy, right? G1, N1, G2, N2 means octet. Whatever quantum numbers you need to define the member of the octet. Which are the quantum numbers that you need to define the member of the octet? You need to define the strangeness, and then you need to define the isospin, right? Then the another octet, the another quantum numbers, your Hamiltonian, and then you take another matrix element. So the only difference is that this Cles-Gordon now is going to be an SU3 Cles-Gordon. I should couple 8 to give all the possible group representations. I will get a singlet, 2 octets, a decuplet, an anti-decuplet, and a 27. I'll do the same thing here. I will come here, and then I say, oh, this is an scalar, and there is 3 transformations, right? So automatically these numbers, these 4 components should be the same, the representation should be the same, and the only thing is that the reduced matrix element, it will depend on the representation. In the same manner that here it will depend on J, there it will depend in either you have 8, 10, anti-10, 27, or singlet. You understand this? And that will be just ICU3 analysis, right? ICU3 analysis. In the same manner that this is just an ICU2 analysis. You do this thing and you don't know what these matrix elements are. You need to know the Hamiltonian to decide, or the operator to decide if this is -3 or +1. So the typical, right? You understand what I mean? For instance, if you do any operator, just G1, G2, or whatever operator. But here, the operator is Weber-Tomosawa. And then what Weber-Tomosawa tells you is, oh, the interaction is attractive in 3 of them, and is repulsive in 1, and there is no interaction in another. And then actually it's telling me that the interaction in the singlet is even more attractive. That's the reason why the second pole, the lambda 38, has an energy which is even smaller, right? So this is a consequence of chiral symmetry. But then you should expect to have the partners, because in an octet, you don't have only the lambdas. You have the nucleons, you have the cascade, you should have the sigmas as well. But just because of the breaking of symmetry, you only see BAMs, right? You got the idea. So in principle, you get everything. Okay? More or less, you obtain the flavor of what is going on. Okay, so I think this can be seen on the lattice, but too much. Okay. I think it's a good moment to stop. Thank you very much for your patience, and I'm sorry for any mistake in particular here. I felt really embarrassed, right? Because this is trivial quantum mechanics. And then okay, when I thought in the office, I thought, well, this is easy, right? But thank you very much, and I hope that you will understand a little bit more the comments of the PDG on the lambda 1405. 2 poles of the scattering amplitude in the complex energy plane between the K-bar and pi sigma threshold. You have a resonance. Well, this is the most important. The origin of these 2 pole structures is attributed to the attractive channels and is determined by the Weber-Tomosawa, right? Okay, and that's by the way, that's the reason why the constitutor quark model people cannot get this resonance, because this is already a pentaquark if you think about that. What is the content of K bar n or pi sigma? 5. So constitutor quark model people can get this if they include these degrees of freedom, of course, also in their approach. Okay. So in the slides, for instance, in this group of slides, you will find things, because I can do the same thing, just considering the decuplet of baryons, and then you get, it's also Weber-Tomosawa, you will get other resonances. And there is another group set of slides that I don't know if they will be available or not in the web page, where I focus, well, I change the strange quark by a chunk quark, right? And then the physics is very similar, right? Instead of the lambda 1405, you have lambda c, and that one is 2595. Okay? Thank you very much for everything.
Okay, now let's begin the exercise that Professor Nieves left with us. Okay, the first one should be this. We want to derive this potential matrix to get these coefficients. And okay, so for such meson and baryon interaction, their potential, their lowest order potential is described by so-called Umberger-Tomozawa term, and that's from the beginning. The Carroll Lagrangian for the meson and the baryon interactions can be described by this Lagrangian. Okay, and for this term, it's just the kinetic term of the baryon of the matter field. Also, here we see that this derivative is not the normal one, it's the covariant one. So here, the covariant derivative of the baryon field is the normal one plus this term. And the U here is just contains the pseudo scalar mesons. It's just equal to Stone bosons. And so how we derive the meson baryon interaction from this one and finally get to equation 6. Okay, let's do this. Actually, this term only comes from the first one, only comes from here. And for the later two terms, here we have two coefficients, two parameters, d and f. Actually, these two parameters should be fixed from some experimental information. But for the first term, it's totally fixed. It have no parameters. It's just have one. It's the f prime, the Pound decay constant. So it is the power of Carroll symmetry. Okay, let's look at this one. And so we want to derive the Lagrangian contains these four particles, and so it's B I. The mass term we just ignore it because it doesn't contribute. And here we take a trace. Also, in this covariant derivative, there is a normal derivative, so we also ignore it. So it should reduce to derivative. Okay. So u dagger partial mu u plus u partial mu u dagger, and its communicator is B. So what we need to do is just expand the u. U is exponential I phi over this. Just expand it. Also, we need the U dagger. Put a minus sign here. Also, it's minus plus blah blah blah. And then we do the derivative, and So the partial mu u should just be so it is quite straightforward. You just go in this direction, and maybe you need the next order, but I think it's easy for you. And here we have gamma mu. Yes. So these, since we have not enough time, I just omit this derivation. It's very easy. And you will quickly get this equation 6, okay? So let's look at equation 6. It contains 4 fields, 2b and 2 phi. And here we have 2 communicators, and then we can do the calculation for the bm to bm. Okay. It should be on. Yeah, okay. So here we know that the B and the phi, they are 3 by 3 matrix because we consider the SU3 flavor space. B is here and the phi is here. So for such calculations, we do not need calculate by hand. It's tedious, but using mathematics or some software is quite easy. And here I prepare one. Maybe small. Okay. Here, this just some input for the display style. It doesn't matter, and we just put all the matrix we have. P3 means this pseudoscalar matrix, and also because we have the partial phi, so we just denote it as this one. Also the bions, also the B bar. We using such input and put them into these trees. For example, here we have B bar dot this phi and partial mu phi, their communicator, just the P3 dot PD P3 minus PD P3 and dot P3. And then we have to communicate with this B, and then take the trees and then expand it. So we have all the explicit terms for these couplings. Now, if we want to calculate this matrix, we just using the corresponding particles as the incoming and outgoing particles, and to take their coefficients and add them up. For example, let's look at this one. It's pi n to pi n. Also, we note that its spin is 1/2, so we should first construct a pi n state with isospin 1/2. Because in this Lagrangian, all the fields are the particle basis, not the isospin one. So for example, for pi n, the I equals to 1/2 this pi n state, we can, using the CG coefficients, to get this value. But what we should pay attention to is that the convention of the isospin. We know that the pi plus, pi 0, and pi minus, it is an isospin 1 multiplied, but it's 1, 1, 1, 0, and 1 minus 1. We actually corresponding to this basis, but because here the pen have some have the antiquark and the U D and U bar D bar. At the quark level, U D and U bar D bar U should be the isospin 1/2 is multiplied, but since these two representation for these two bases, they are not the same, but they are similar with each other. So we should do a similar transformation, and here we need to do a basis transformation. That means, in conclusion, UD corresponds to this one and this one, but D bar U bar, we have a sign difference. You can either put the minus sign here, or you can put this minus sign to this place. Anyway, if you use this convention consistently, you will get the same result. So in conclusion, there for pi n fields, there's similar conventions. That means here we should put a minus sign here. So pi plus corresponds to the minus 1, 1, not the plus 1. Also, you can put this minus to here, but the final result should be the same. So, for example, from the CG coefficients, we know that these two coefficients is square root of 2 over 3, and this one is minus 1 over square root 3. But since pi plus here has an additional minus sign, so finally, what we write should be minus and minus, not plus minus. Otherwise, if you did not take this minus sign, you will find that for the pi n, we know that for isospin 1/2, it has two states. One is 1/2, 1/2, and 1/2 minus 1/2. So what I wrote here is 1/2, 1/2 is this state. And you can also write down this one. If you did not consider this minus sign, you will find that these two states have different potential. It is not allowed because this strong interaction is isospins satisfy the isospin symmetry. That means the state in an isospin multiplate, they should have the same potential. So it's just can be a cross check to check whether what you did is correct. And after this, we can just extract the Lagrangian, extract for example, the pi plus n to pi plus n term from the Lagrangian, and also the pi 0p, pi 0p from the Lagrangian, and also the cross terms, and then add them, sum them up. So here we get the factor 2. Also, let's look at this matrix. Here is -2. Whoa, what's going on? Because what I calculated is the scattering amplitude. It's actually usually it's S equals to 1 plus IT. And what is shown in Professor Nieves' slides, its convention is S1 equals I minus IT. So using this convention, we can get the Liebman-Schwinger function like V plus VGT. If using this convention, we'll get T equals V minus VGT. That means in this convention, this V, let's say V tilde, okay? This V tilde and the V here has different sign. Usually in the hadron spectrum or in our fields, we usually using this convention. Why? Because this V, in this convention, the minus V means attraction, and the plus V means repulsive. So it's consistent with our feeling that a negative potential means they are attractive. But anyway, this convention did not affect the final results. So I should put a minus sign here because what I calculated is this one. We should put a minus sign to obtain this. So we got the 2. Similarly, for eta n, since eta is spin 0, so the only possible one is the 1/2. And the coefficient for such term is 0. And when we look at this matrix, eta n to eta n is just 0. Also, k sigma to k sigma or k sigma to pi n, k sigma to k sigma is here, is also 2. Pi n to k sigma is here, minus 1/2. It's the same. We reproduce the results in Professor Nieves' slides. Okay, so all the others are in the same procedure. Maybe you can do it by yourself if you are interested. Okay. So using this method, using this way, you can get this S equal to 0. This means strangeness, and S spin 1/2. You get this matrix, and you can get the other T equals to maybe 3/2, some other multiplies, and you can find the poles of other channels. That's the basic logic. So, do you have any questions about this part? Yeah?
So, do I get that correctly? We get the prefactor, we get from the structure of the Lagrangian, and then the matrix we get from this spectroscopy.
Yes. Yes. Correctly. Exactly. Okay, now let's move to the next one, also the last one. Okay, 5 minutes. Okay, I will be quick. Okay, stretch the logic and the problem is Q P minus Q. It's to show that this loop function, also known as the propagator, this is the expression for the loop function of the propagator. It is t equals to v1 minus vg, and t inverse equals to v inverse minus g. And so what we want to show is that the t inverse equals to minus g inverse, to show that it is proportional to the momentum. So to do this, we should do this integral of Q0 first. And blah, 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 like this. Here's an I. And we can see that here we separate the Q0 square minus E1 square I epsilon and the P0 minus Q0 square minus M2 E2 square. Okay, we know that there are 4 poles of Q0 in the complex plan of Q0. It's real Q0 and the image Q0. The poles located at, from this one we have Q0 equals to E1 minus I epsilon plus minus. So this pole location is one is here, another one here. Also for this is Q0 equals to P0 plus minus E2 plus minus I epsilon. Okay, this. So this pole position right here and another one here. So to do this, we use the loop integral. We integrate on the real axis, and then we add a half circle. We know that this half circle, the contribution is 0 because here we have a power of Q04. Q04. Such is very surprised. So this contribution is 0, and we just use the Kersey integral principle. We have 2 contributions of these 2 poles. And okay, we just take this residue as these 2 poles and get rid of the Q0 integral. So I will skip the details and also some factors. The final result will be E1 plus E2, E1, E2. Here is P0 plus E1 plus E2 and P0 minus E1 minus E2 plus A epsilon. Okay, also this integral can be separate as the angular part and the radial part. From this expression, we are almost done because we want to look at its imaginary part. Okay, so for the, because E1 and equals to M1 plus Q square, E2 equals to M2 square plus Q square. This one, which one? Here? This? No? Okay, I think it's correct. Okay. And this, because this does not have pole, because P0 is positive and E1 and E2 for real Q is also positive. So this one do not have pole, that means it will not contribute to the imaginary part. Only contribution is from this term. We use an expression that it should be the principal integral minus I delta x. Yeah, if we do this integral, we should, it is related to this one. That means this one contributes to the real part, it doesn't matter, and also only left is the imaginary part is the delta x. That means we should replace this one as an minus I delta P0 minus E1 minus E2. And using these two expressions and this delta function, and then integrate over the Q. Yeah, okay. We will get directly to the final result. It's just the proportional to K, to the momentum, the Earnshaw momentum. This is the Earnshaw condition. Okay.